Thank you very much. It's great to be here again. And so this is based on, this is based on a paper from the summer. It's going through the review process now with my co-authors here. I just want to highlight Levi here because he was a UH undergraduate at the time. Oh, Levi, yeah. So I think I have to aim at this to, okay. Okay. So, as you all know, dwarf galaxies are a prime target for dark matter indirect detection searches, where you search for dark matter and the products produced by dark matter annihilation. And one of the reasons why they're such a prime target is because they're believed to be dominated by dark matter. So you expect to get a large signal from there. You also expect to get less background from other astrophysical processes, just because there isn't a lot of ordinary matter in these dwarf galaxies. Are dominated really by the dark matter. And so one of the things you like to look for are the photons which are produced by dark matter annihilation, because they point back to the source. So you use something like the Fermi telescope, pointed at some dwarf spheroidal, and measure the flux of high-energy gamma rays, and look for some excess above what you expect from the background. So many of the newly discovered dwarf galaxies are what are called ultra-faint dwarf galaxies. So these are galaxies which produce very little stellar light. And for many of these, there might only be a dozen or so identified member stars of your ultra-faint galaxy. And that's kind of what you would expect, because one way to think about it is, if it was easy to discover many member stars, then we would have found it a long time ago. The fact that we're only finding it now means we're probably only going to start off finding a few of these. No, they're actually detected by stars. So, for example, these new observatories like the Rubin Observatory, the idea is just that as you can see more stars, you can see clusters of stars, you can look at their velocity dispersion, and see if they look like they're clustered together. And so, we expect as these new observatories come online, that the pace of discovering these new dwarf galaxies, especially these ultra-faints, is going to increase. And if any of these are nearby, then they could be a great target for indirect detection. But we need some way to learn about them. And in particular, what we want to learn about is a quantity called the J factor. And we can think about this as the astrophysical input to this calculation of how many photons we would get from dark matter annihilation. Essentially, it's kind of a measure of the dark matter content of this galaxy. And so the annihilation rate is going to scale with that. So that's the thing which we want to find. And so, as an example of why this can be important, I'll use the example of Ursa Major III unions 1. And so this actually has this kind of weird name because it's not entirely clear if it's really a dwarf spheroidal galaxy or if it's a star cluster. Excuse me. And so the convention is, if it's a dwarf spheroidal galaxy, you name it after the constellation it's found in, and you index it with Roman numerals. But if it's a star cluster, then you name it after the collaboration which found it, and you index it with an Arabic numeral. And so one reason why this could be a very important system is because it may have the largest J factor of any known dwarf spheroidal galaxy, mainly because it's only about 10 kiloparsecs away, so it's really close by. And so the people who discovered it, yeah, you expect it to be a lot of dark matter which is binding this thing together, whereas with a star cluster, yeah. Yeah. Yeah, well, honestly, since I'm not an astronomer, I'm just kind of using the words we use. But I think basically a star cluster is, generically, a star cluster, globular cluster, any of those kind of things which is just dominated by the stellar matter. Yeah. And so, the people who discovered this, they kind of went through the process of estimating what the J factor would be, using some of the techniques which I'll talk about later, like spherical genes modeling. And they get an estimate here, which, which if you took this estimate could be the largest of any known dwarf spheroidal. Now again, there's a lot of salt attached to this, a lot of grains of salt, because you can see the uncertainties are large. These are uncertainties in the exponent. But if I took the central value even close to seriously, I said, let's say this really is a dwarf spheroidal galaxy, the J factor really is something like, this central value, then you could say, okay, let me just look at what the Fermi telescope sees when it looks in the direction of this dwarf spheroidal galaxy, look at the observed gamma ray flux. Using this J factor, find a bound on what the dark matter annihilation cross-section could be. And what you find, even taking the central value, is that you improve by a factor of 10 on the bounds on dark matter annihilation, which you get from all the other dwarf spheroidal galaxies combined. So there's a lot riding on, is this really a dwarf spheroidal galaxy? Can you really sort of improve the essence of this J factor? And is it even close to that central value, or was the central value way off? So there can be a lot riding on how much we can get to know and understand some of these new dwarf spheroidal galaxies which could be found, especially if they happen to be nearby. And so, how can we learn about these targets? One way we can think about it is, to figure out how much dark matter is in one of these targets, what we need is the density of the dark matter as a function of your position in the halo. And so if you think about sort of, adopting some parameterized function for the dark matter density profile, what you need are the parameters of that profile. And often one which people use, and which I'll describe in a little bit more detail later, is the NFW profile. What you have are the positions of the stars, the identified number stars. And really what you have, for the most part, is those positions projected onto 2 dimensions. Because it's hard to precisely measure the distances along the site, along the line of sight. It's really easier to measure the angular distances. You also have the velocities of the stars. But again, there you mostly have the velocities along the line of sight, which you can get from redshifts. It's hard to get the transverse velocities. So what you need is a way to get from what you have to what you need. And the basic idea is just to use the stellar data to determine the gravitational potential you'd need to keep these stars confined. Mm-hmm. You can use spectroscopy, but it's hard to get the individual. So let me give you the example of Ursa Major. What you'll do there is you'll say, let me take the brightest stars, okay, and then try to fit, where they are on your main sequence, do some fitting, and then average all of them to find the distance to the system. Okay, so that's how you get that. It's about 10 kiloparsecs away. But again, that's like combining all of them to get one distance, not the differential distances of each one. Right, the individual distances of the line. So yes, you have like a distance to the object. But if I want to find the positions of the stars themselves, the individual stars, I can measure the transverse distances. But the individual distances of the particular stars, that's hard to measure. Yeah. But whereas the transverse one is easy to measure. Excuse me? Yeah. So one way to kind of think about it is, I'll use that example of Ursa Major III. They basically take, a handful of the bright stars, fit where they are in the main sequence, and try to use that to get an average distance to the system. But even if you could somehow use that to get those individual stars, that's not even all the stars. That's only like 4, right? So it's like you have averaged 4 stars to get the distance to the system, but the individual stars, you don't even have for those 4, let alone for all the other ones which you didn't measure. Mm-hmm. So that's what Gaia tries to do. So you can start doing that with Gaia. Right now, Gaia isn't really in this game yet. So with their, I shouldn't say that yet because I haven't followed as much on Gaia, but like their Gaia data release 2 and things like that, you would try to get the distance along the line of sight using the parallax, but the measurements were not that great. I think data release 3 and the upcoming data release are supposed to improve on that a lot. So I think with that, some of this game might change. But for most of the things people are doing now, you're not yet able to do that. Mm-hmm. Yeah. Well, yeah, I guess the idea, I guess the thing is that when you find a new dwarf, you're probably looking with an instrument which has, which is, better than Gaia. Because Gaia's going to have this wide field of view. It's a survey, right? It's not going to be the kind of focused search which you might use when you're finding one of these. So, yeah. Yeah, and so the idea then is to take the stellar data, determine the gravitational potential you need to keep the stars confined, and then figure out what dark matter profiles you need to generate that gravitational potential. Excuse me? Mm-hmm.
And then how we are going to predict
Okay, so it turns out that half of astrophysics, I think, is performing an able integral transform. So it turns out that projecting from 3 dimensions onto 2 dimensions is what's called an able integral transform. And like all good integral transforms, it has an inverse. So if you just assume something like spherical symmetry, from the 2D projection, there's a 1-to-1 mapping to the appropriate 3-dimensional thing. So you can actually do that in 1-to-1 way. But I won't need to use that. All that is done in the background, but I won't discuss it more. But it turns out you can go from 2 to 3, the 2-dimensional profile to the 3-dimensional one, almost 1-to-1, just because it's just an able integral transform and it has a unique inverse. So the algorithm of the rest of my talk was going to be, how do we learn about dark matter distributions from GEANS modeling? How do we relate what we learn about them to dark matter annihilation by recovering the J factor? And finally, what can we say about applying this to these ultra-faint dwarfs? And can we replace a lot of this GEANS modeling machinery with some simple scalar relations? So I'm going to start with a few assumptions, which you can think of as approximations to what's going on in one of these ultra-faint dwarfs. I'm going to assume that the matter distributions are strictly symmetric. And I'm going to assume that they're static. So the time average distribution is a good approximation to what you see today. I'll assume that the only force is gravity. So if these assumptions apply, I can essentially treat this like a classical mechanics central potential problem, which I can just get from a text. And in particular, what I'm going to end up using is Liouville's theorem, which basically tells you that a phase space density is time translation invariant. And what that's going to directly lead to is the spherical GEANS equation. And that's kind of the starting point of this GEANS model. And so what I'm going to start with is applying Liouville's theorem to the stellar phase space density, which I can think of as the number of stars per unit spatial volume, per unit volume in momentum space, or equivalently velocity space. And so for a static phase space density, then Liouville's theorem just amounts to saying that the Poisson bracket of my phase space density, which I'm denoting as F star, with the Hamiltonian is going to be 0, where this is my Hamiltonian, and phi is my gravitational potential. So that's where the dark matter content is entering into this. Because for an ultra-faint dwarf, I think the gravitational potential will be mostly dominated by the dark matter. So to get to the spherical GEANS equation, all I really have to do is just multiply Liouville's theorem by the radial momentum, and then integrate overall momentum. And that leads to this equation, where rho star is the spatial density of the spatial profile of my stars. So I can think of it as the stellar phase space density just integrated over momentum. So stars per unit volume. Inside the quantity in the angle brackets is my radial velocity dispersion as a function of my 3-dimensional distance from the center of the halo. My gravitational potential is here. And this parameter beta star is called the stellar anisotropy parameter. So if the star's velocities were as likely to be in any direction as any other direction, then this quantity would be 0. But in general, the stars could be more likely to have radial velocities or tangential velocities. And so this spherical GEANS equation becomes the starting point of this. And one thing I always like to note about this is that this is one of those examples where using the Hamiltonian formalism isn't just another way to solve a classical mechanics problem. It'd be a real pain to try to solve this without using Hamiltonians. And I always like this phrase from Binet and Tremaine, a reader unconvinced of the usefulness of the Hamiltonian formalism to try deriving the spherical GEANS equation without it. Although I think they just use some equation numbers here instead of that phrase. But the idea here for what you do with this, how you use this for GEANS modeling, is you just start off with, say, an ansatz for the dark matter density distribution, say this NFW profile, and you use that to see what the gravitational potential would be. Similarly, you have an ansatz for the stellar density profile. And I mentioned some of the ansatz astronomers commonly use. And you take some ansatz for the stellar anisotropy parameter. Once you do that, this thing just becomes a first-order ordinary differential equation for the radial velocity dispersion. And so you can solve it exactly. So what you do is you solve it exactly, you project that onto a line-of-sight velocity distribution using these Abel integral transforms. So you get your line-of-sight velocity dispersion as a function of the two-dimensional distances. And you just compare that to the data. So what is the likelihood of the data given that ansatz? And so as you vary this ansatz, you can try to maximize the likelihood. And that allows you to constrain the dark matter parameter, the dark matter profile. Excuse me? Right, but for a large dwarf, you would include them both. But for an ultra-faint dwarf, I can assume that this is just dominated by the dark matter because there aren't that many stars in this anyways. For an ultra-faint dwarf, I know that.
No, but if it's a star cluster, then it's dominated by those stars.
Oh, right. So this is if I'm assuming that it's a dwarf galaxy, yeah. Mm-hmm.
But what is the fitting? How much is the deviation between lone star and no dark matter when you're fitting with the actual activity position?
So if let's say I'm doing a large dwarf, okay? Then what I would do is I'd say, okay, I've seen some stellar light, and I have some estimate which astronomers know how to do for what the mass to light ratio is. So that gives me an estimate of the stellar mass of this. So there isn't as much degeneracy between those two because I won't have as much freedom in the mass to light ratio. Now, for one of these ultra-faint dwarfs, again, what I'd say is if I really think that this is a dwarf, so I said, okay, and usually the way you look at it is you say, okay, what's the velocity dispersion of these things? Is it something which would seem to require a lot more mass than what I would expect from these stars? Then I would say, again, I don't have that much uncertainty in it because, I'd say essentially I can ignore the stars for that purpose. But again, there will be places in the middle where where you have to worry about it. So the degeneracies which come into that, I'm going to get to that later on. Mm-hmm. No. So one way to look at it is once I've made some ansatz for this. So I pick my NFW profile, I pick some parameters, and I'll describe that on the next slide. I pick a few values for this. Yeah, this is just a first order ordinary differential equation. I can solve it exactly, right? So I don't have to make any assumption about it. And so the idea is that as I then vary the parameters, that vary my solution, I'm varying the likelihood of my data. And so you want to maximize that and use that to constrain your parameterization. Oh, okay, so I've assumed that it's, gravity only. So if it's SIDM, let's see. If it's SIDM, it probably doesn't work, right? Exactly, right? And the reason is because what I've thrown in here, I've assumed that the Hamiltonian only has a gravitational potential, okay? So if I want to do SIDM, I would have to kind of fiddle around with it a little bit. Yeah. Mm-hmm. I mean, I could probably modify it for that, but this is not what I've thrown in here yet. Oh, I'm sorry. Oh, right. Yeah. Oh, yeah. I'm sorry. I was mixing up if I was using. So you also use Leopold's theorem for the dark matter distribution. If you want to understand that, if you were trying to solve the dark matter velocity distribution, and in that case it matters. In this case, actually, yeah, you're right. It doesn't matter. So if let's say the dark matter is collisional, okay. Then what it's going to affect is what my profile is. So I can still use this because it'll affect the stars. What it'll affect is what's the parameterization of the profile I'm using. So for example, people who do, I mentioned the NFW profile. People who use the NFW profile say, well, when I do simulations where there's no self-interaction, there's only gravity, I tend to get these cuspi profiles. They kind of look like they could be NFW, right? But when people do simulations where they include, self-interaction and all the energy transfer which comes with that, you get these things which are more core. So you can try to marginalize over all of them, and then that's a lot more degeneracy, okay, which is hard to constrain when you have an ultra-faint dwarf and you only have a few dozen data points anyway, or like a dozen data points. But if you just assume that there's only gravity, then you're kind of saying, okay, well, I'm assuming that it's not self-interacting, so I don't get that kind of chord profile. But otherwise, if you did a chord one, you could still, for the understanding the stellar distribution, you could still use this. Yeah. Okay. Now, people also try to use Liouville's theorem to understand the dark matter velocity distribution. And you can do that, but that becomes harder when you have self-interacting dark matter, because now the force isn't only gravitational. So you don't know what that potential is. Excuse me? I assumed it's spherically symmetric. Now, it doesn't have to be. So you could do that also. And there are ways to modify this. But if it's an ultra-faint dwarf, you only have a dozen stars. So it's hard to... one way to kind of think about it is just at a naive level, what you would say is that if the number of parameters is more than the number of data points, we're not going to be able to constrain anything. Right? So if I only have like a dozen stars, the more parameters I add, the more I'm just going to say I don't know anything about it. Right? Mm-hmm. Yeah, Liouville's theorem is valid in general, but being able to apply it to the, I guess one way to look at it is, Liouville's theorem would be valid in general, but being able to write the potential as spherically symmetric, that's something which I would have to work with. Yeah. Yeah, you have something non-spherical, yeah.
I think we got the differential equation only in terms of BR squared because we assumed this very case.
Yeah.
That is we get V theta equation and the V phi equation.
Yeah. Mm-hmm. Right. And so the starting ansatz I'm going to use is to assume, again, the dark matter has an NFW Navarro-Frank-White profile form, which is what people find when you look at gravity only as the interaction. So that's what you tend to find in large N simulations. And so there's a scale radius and a scale density which parameterize it. And one way to think about it is that when your distance from the center is much smaller than the scale radius, then basically this profile looks like 1 over r. Once you go outside the scale radius, it drops much more rapidly, like 1 over r cubed. Now, for the stellar distribution, I'm also going to take one of these common parameterizations called the Plummer profile. And so astronomers tend to find this is a good fit to spheroidal galaxies. And again, it has an overall density normalization. And the other parameters characterize it as what's called the 2D half-life radius. And so the idea is that, again, since the things we can measure the most are these kind of 2D projections, you can think about this as if I projected this three-dimensional profile onto 2 dimensions, then this is the distance inside which roughly half the light would come from. Or, a rough equivalence of which half the stars would sit inside. Okay? Or you can think about it as like if I didn't project it, the radius of a cylinder, which would contain about half the stars. And so the goal is that you want to find, sort of posterior distributions on rho s and rs, the parameters of your dark matter distribution. And typically what you end up finding is that the scale radius is significantly larger than the half-life. And, it's kind of even what you'd see in the Milky Way. You have this large halo, but most of the stars tend to sit well inside the center of it. And so what you want to do is to go from these posteriors to the J factor. And so the J factor, you can think about it as essentially part of the astrophysics which tells you how many photons you're expected to get from dark matter annihilation. So if I assume that my dwarf is small compared to its distance away from us, then you can write an expression for the differential photon flux. I won't go focus on the details of it so much as the color coding. In blue, I have all the factors which depend on the particle physics of dark matter, like its mass, its annihilation cross-section, the differential photon flux produced per annihilation. And I can factorize all that out in this phi pp factor, this factor which depends on the particle physics. The astrophysics pieces, like the distance to the dwarf, the density profile, this NFW profile, I can factor out into this J factor. Okay? And so phi pp is going to be the same for every target in the sky I look at. The J factor is specific to that particular halo. And so the idea of that is if I can use Fermi to constrain the actual gamma ray flux, so I can constrain this from Fermi, then I can try to use that to constrain the particle physics. But to do that, I need to know the J factor. There are no stupid questions, only stupid answers.
So, when we took out the averages sigma v out of that exit, so the velocity of that point of particle also changes as the distance from the center of the
Right, so I have made one simplification here, which is I have assumed, and I didn't get into it because I thought it would take a little bit far afield. I've assumed that this is S-wave dark matter annihilation, in which case sigma v is independent of velocity. Now, if I had not done that, then in general what I would do is, here we go. What I might do is write sigma v is equal to sigma v naught times v over c to some power n, where n might be 2 for p-wave annihilation, 4 for d-wave annihilation, for Sommerfeld enhanced annihilation, and the Coulomb limit, it would be -1. And what I would do is, this factor here would be what goes inside phi pp, and this factor here would go in here, and in fact, actually, in doing that, I'd have to I'd have to have integrals over the velocities, I'd have to have the phase space density in here, and those integrals over velocities, the phase space densities, these would all go into an effective J factor, which now depends on the power law dependence in here. Okay, and so in the case where n is 0, it reduces to this, and since that's the only case I'm looking at, that's what I left there.
So here's the velocity distribution function you actually derive profile.
No, I'm assuming the velocity distribution will have a profile, but for S-wave annihilation, it's not going to matter. Right, it doesn't depend on that. Now, if I was doing something like, P-wave or D-wave, then I'd have to use Liouville's theorem again and go through some whole thing to figure out what the dark matter velocity distribution is. So then I'd have to do that whole thing. But for this case, if I just take the S-wave, then I don't have to worry about it. So for simplicity, I'm just focusing only on that case. On the previous slide. I'm sorry, this one? Yeah, well, maybe I should phrase it this way. And again, I'm not an astronomer, but this is my understanding, which is, when you look at these spheroidal galaxies, this is a reasonably good fit. Now, it's not the only fit people use. There's something called a King profile, there's some other profiles, but this is one of the most common ones which people use, and it seemed like a reasonably good fit. You can think of it kind of like NFW versus INASTR or all this stuff for dark matter. Yeah. So then, how do you get from? So what you want to then do is to go from these posteriors on ρs and rs to the J factor. And so one way to think about how you would do that, right? You know that this J factor, this is kind of the expression we have for it, it's going to go like 1 over d squared. And since I'm integrating this NFW profile over the whole size of the dwarf, the only thing you can depend on is the parameters of the profile, ρs and rs. And the dependence on ρs and rs is kind of fixed by dimensional analysis. Since you know the units this thing has to have, it kind of has to go like ρs squared rs cubed. The only thing you don't know is what's the coefficient out front. And for an NFW profile, you just have to do dimensionless integral, and you get 4 pi over 3. So to get the total J factor, what you need is ρs squared rs cubed. And so if you just find the posterior on that quantity from your genes modeling, and that gives you the posterior on the J factor. That's how you get these J factors from genes modeling. Excuse me? I'll get to that in a second. So I think on the next slide, actually, I'll get to that. Right. So one question we can ask is, how much does genes modeling actually tell us, especially for something like an ultra-faint dwarf? Does it actually give us all the information we need for the J factor? And this will kind of get to the question you're asking. So what I've plotted here is rho as a function of r for this NFW profile. So inside the scale radius, it goes like 1 over r, Once you get outside the scale radius, it falls off, more rapidly, like 1 over r cubed. But since the J factor goes like density squared, it falls off very rapidly out here. So there's very little dark matter annihilation outside the scale radius. Now, back to your question, like you said, instead of integrating all the way to infinity, I should really integrate out to something like a tidal radius. But the tidal radius is typically much larger than the scale radius, which means there are a lot of things that it matters for. If I want the total mass of the dwarf or things like that. But if I want dark matter annihilation, then it actually doesn't matter much, because by the time I got to the tidal radius, there's no annihilation anyway. So, really somewhere around here is where dark matter annihilation starts to become no longer relevant. But, here's probably where my stars are going to be, where I'm assuming the half-light radius is kind of small compared to the scale radius. So one question is, what can I actually see with Jeans model? Okay? Because these stars are sitting inside that 1 over r part of the NFW profile. So as far as they're concerned, this density profile just looks like rho s rs over r, that 1 over r behavior. But remember, if that's what my stars are seeing, and that's what the gravitational potential from dark matter is just being generated by this density profile, then that's all Jeans modeling can see. All it can see is the effect of stars on the gravitational, the effect on the stars of the gravitational potential. If this is this is what's generating that gravitational potential, there's only one parameter, rho s rs. That's the only thing I could possibly reconstruct from Jeans modeling in this lecture. But that's not enough to give me the J factor. It doesn't even have the right units of the J factor. So I can't use that, or no powers of that are going to give me the J factor. There's one parameter I'm missing. And we can kind of see almost from this picture what it is. Essentially, we've got the density profile here, which means the density square part we can do. We just don't know where to stop the integration. Where does it fall off? And the annihilation region ends. So it's kind of the edge of the integration region is what we're missing. Now let's say the half-light radius was a bit bigger and I had enough stars out here to tell where this was ending. Then I could measure the scale radius, and that essentially tells me the edge of the integration region. On the other hand, let's say I don't have stars which go all the way out there. In some sense, what really sets the edge of the integration region is just my apparatus, just my experiment. Because what I'm really doing is I'm looking with the Fermi telescope and saying, look at all the photons coming from within half a degree or 1 degree of the center of my halo. And that might subtend, say, a size like this. Now, maybe the scale radius is much larger, and maybe there's a lot of annihilation going on out here. It doesn't matter, right, because I'm not even looking for it. So this region just controls the size over which I'm integrating my J factor, whether there's annihilation coming outside that or not. So in that case, what sets the edge of this integration region is really the size of your aperture. If I denote that size as Rn, let's say it's small compared to the scale radius, and I only integrate my annihilation rate out to there, again, my answer is almost fixed by dimensional analysis. I'm going to get something which depends on this parameter I can get from Jeans modeling, rho s rs, in this case squared. And another dependence on a parameter which, maybe I could have determined from the stars if I had a large enough half-life radius. Or maybe it's just set by my experiment. Yeah. So for example, if I'm looking at it with Fermi, and I say, well, it depends on the experimental setup. Let's say I look with Fermi, and I say my analysis is going to be to look for all the photons coming from, all the gamma rays coming from within 1 degree of that. Then at that distance, 1 degree is going to subtend some radius. And I'm really looking at the annihilation rate in that radius. There could be an annihilation outside, I'm just not going to integrate over that. Yeah. Oh, right, they can, they can see a lot, but usually in their analysis, what they will count is the photons coming from within a certain aperture, right? So they then compute the J factor over that aperture, right? So they might compute the 1 degree J factor or something like that. There might be more photons outside, but they don't include that as part of their analysis, even if they see it. Yeah, I've used stellar motions to determine the dark matter profile, yeah.
But in our galaxy, we also use gas. That is based on the different
Mhm.
That's
Right.
still-
Yeah, there's very little gas.
Okay.
Mhm. Excuse me? Yeah. Mhm. So usually, right. So I haven't gone through experimentally how they would convolve all this with the point spread function. Generally, I think what they do is, if I a typical Fermi analysis, they might go from 1 to 100 GeV, which is the range over which the effective area is roughly constant. And at 1 degree, I think around 1 degree, less than 1 degree is about the size of the point spread function. So roughly looking at that size means you're not going to lose much in terms of things being moved in and out of by the point spread function. At higher energies, it becomes even less. So roughly that's how they set that 1 degree. Although, in a real analysis, they might do something more complicated than that. But as a rough estimate, that's roughly what they do. Were you asking something? Oh, okay. Okay. Right. So how can we figure out if Jean's modeling can actually tell us what the scale radius is? So one way to do it would be just to solve the Jean's equation exactly for a few examples. So what I'm going to do is I'm going to assume a Plummer stellar profile, an NFW dark matter profile. And again, since I'm looking at ultra-faint dwarfs, I'll assume that the dark matter is dominating the gravitational potential. I'm going to fix RH and rho s RS. Okay, so I'm going to fix, the size of the half-eye radius, the form of the dark matter distribution here, but I'm going to vary RS. Okay, how far out this annihilation region goes. I'm going to pick 2 particular examples. I'm going to let RS equal 4RH, so somewhat larger than the half-life radius. And I'm also going to take it much larger than the half-life radius. So I'm going to take RH over RS effectively 0. I'm also going to take various choices of beta, either positive or negative. What I'm going to do then is just solve for each of these choices in every ansatz. Solve the spherical Jean's equation exactly to get the radial velocity dispersion. Do the appropriate able integral transform and project this onto a line of sight velocity dispersion as a function of the 2-dimensional radius. And then just plot that in terms of the quantities I've held fixed. And so what you can see is that at small radius, these curves are all kind of on top of each other because the degeneracy with beta star, I think this is a question you were asking about earlier, that degeneracy basically swamps everything else. Okay? So if I see the stars here, it's hard to tell anything about, from there, about, what the scale radius was, because it's all, subsumed in the uncertainty in beta, which is something I don't know. Where that really clarifies is if I get stars way out here, where all the curves where RH is small compared to RS kind of cluster together, and where RH is, say, 1/4 RS, all cluster somewhere else. If I could see some stars out here, I could tell the difference between these 2 scenarios. This is the line of sight velocity dispersion in units of 4 pi g Newton rho s RS RH. So these are the quantities I fixed. Right.
So why is this something that is negative?
No, this is a solution to the spherical Jean's equation. So there's some data. But what I'm saying is, having taken this ansatz, where I've just picked these parameters, I now have everything I need to solve the spherical Jean's equation exactly. I get an exact solution, project that onto the line of sight, and then just plot it. Mm-hmm. And so I'm fitting the data to this, right? So what I'm seeing then is that, regardless of what beta is, these curves all line up like this once I get to large enough R. Okay, for the case where RH is much smaller than RS. And where it's 1/4, they all line up down here. Stellar anisotropy parameter. So if I had some stars out here, then I can tell the difference between these scenarios. But we can also see that to get some stars out there, I probably need to identify a lot of stars. Because what I plotted down here is the fraction of stars for this Plummer profile, which lie inside this radius. And so once you get out here, you can see most of the stars are already inside. So to identify a few stars here, I probably need quite a few stars, in order 20, 40 stars. Okay? Mm-hmm. Mm-hmm. So this is where RH over RS is small, and this is where RH over RS is 1/4. So small means it's set to 0. So, again, we said that we probably need a lot of stars to figure out where the scale radius is. But the expectation is that for new dwarf spheroids which we find, we're probably only going to have a handful of stars. Well, one way to think about it intuitively is that, I guess one way you can kind of think about it is that if RH is much less than RS, then when you're going out here, as you're going out here, your density, you're still in the 1 over R region of your density, not the 1 over R cubed. So as you go out, the mass keeps growing and growing. It's growing much more rapidly. So there's a larger gravitational force. You have more enclosed mass. So the idea is that as you go farther and farther out, the force from the dark matter pulling on your stars is going to be larger. So you might get larger velocities. Intuitively, it's kind of like that. Although you can just solve it and see. So the question then is, if you only have, say, order 10 stars or so, what's the point of genes modeling with so few stars? Because you can't find the scale radius anyway, which is the thing you need to get the J factor. The one quantity you can find is this quantity rho s RS. But it turns out you might be able to find out without even using genes modeling at all, just using a simple scaling relation to some coarse-grained stellar observables. Okay. And so that scaling relation, is what's called the half-light mass estimator, which is something which these authors described a few years ago. And basically, that's a relationship for the total mass contained within the 3-dimensional half-light radius. So this is, imagine you didn't project your Plummer profile, and you just said, what is the radius of a sphere, which produces, half the stellar light, or, equivalently, which contains about half the stars. And find the total mass contained in this, okay, which is dominated by the dark matter. So you can think about this as a dark matter, a parameter, or an observable, or I should say a variable, which measures the dark matter content of this. And the scaling relationship relates this to, again, the 3-dimensional half-light radius, and the line-of-sight velocity dispersion averaged over all the stars. Okay? And so what's nice about the scaling relationship is that these kind of coarse-grained stellar observables don't require any detailed knowledge of all the individual stars. They're just some numbers which are usually in a table somewhere. The other nice thing about the scaling relationship between the dark matter variable and your stellar variable is that, what these guys argue is that up to order 1 factors, it's largely insensitive to variations in the things we don't know. Like, what's the precise form of the stellar profile? Is it really a Plummer profile or a King profile? What's the stellar anisotropy parameter, which we don't know? So all those things which we don't know, which were giving us all these degeneracies in genes modeling, that only causes this to vary by an order 1 factor. I'm sorry,
profile for velocity dispersion function for the dwarf.
Mm-hmm. Oh, I'm going to give you an example on the next slide, so maybe that will answer your question. Yeah, well, it's the total mass, but for an ultimate dwarf, it'll be dominated by the dark matter mass. So the thing is that this quantity is something which should be well constrained by Jean's model. Okay? It shouldn't have all those degeneracies which come with, say, the stellar anisotropy parameter, those things which we don't know. But we also know that there's really only one quantity which I should be able to get from Jean's modeling in the case where the scale radius is really large, which is rho SRs. Which means that what I get from Jean's modeling should just be the same as what I get from the half-life mass estimator. Okay? So at some level, in this case when the scale radius is really large, I should just be able to replace whatever I learned from Jean's modeling with just this half-life mass estimator. And we can illustrate this by just solving the Jean's equation in a particular example. So let me go ahead and take the case where I'm just going to set the stellar anisotropy parameter to 0. Now I can do that because the half-life mass estimator is supposed to work, up to order 1 factors for any choice of that. So I can make a simple choice, just as an illustration. I'll assume that dark matter dominates gravitational potential, what I expect for an ultrafaint. And I'll take the dark matter profile to be an NFW profile. And I'm going to take the scale radius to be large compared to the half-life radius. So the dark matter mass contained within radius r, I can then just write in this simple form here. I have this 1 over r, and when I integrate over the volume, I get an r squared. And here's my parametric dependence, rho s and rs. Now, I can go ahead and then just write the spherical Jean's equation. It simplifies a lot because the potential term becomes really simple. The stellar anisotropy term, that vanishes. So I just get this expression here. And I can just write down the exact solution for it. The exact solution to this equation is given right here, where these parameters come from the dark matter profile, and now have an integral over my stellar profile. For my stellar profile, rho star, I'm going to take a Plummer profile. And I'll note that from a Plummer profile, the 3-dimensional half-life radius is about 30% larger than the 2-dimensional half-life radius, okay, which I'll always just denote with RH. So if I plug that in, the thing you'll note, which is true for the Plummer profile, and also for all, King profile, all the other ones, is that there's only one length scale in it, which is the half-life radius. R dependence only comes in as a ratio of R over the half-life radius. The half-life radius basically sets the scale. Which means this entire integral is just going to be RH times some dimensionless function of R over RH. So my expression for the radial velocity dispersion, all the units are going to be in this factor out front. A factor which comes from the dark matter profile, the G Newton rho s RS, and then the half-life radius parameter. So what I want to do with this is I want to do my able integral transform, project it down to a line of sight velocity dispersion as a function of the 2-dimensional radius, and average over the entire profile. But the key is in doing that, I'm never introducing a new length scale. I'm just taking a bunch of dimensionless intervals. So I can do that on both sides. On the left-hand side, I'll get the line of sight velocity dispersion squared, line of sight velocity dispersion. On the right-hand side, I'll just get this factor times a number, which comes from doing these dimensionless integrals over this function. And for the Plummer profile, this number happens to be something like 2/3. So now I just have to solve for rho s RS, moving everything else to the other side. I have my line of sight velocity dispersion here. My RH and G Newton go down, and I get this expression. So you can kind of think about this as solving for the one parameter Jean's modeling is supposed to be able to give me, okay, for a particular choice of my velocity dispersion. Or, the stellar anisotropy. This is what I get. And I can compare that now to the half-life mass. Because the half-life mass is just what this mass is when I plug in the 3-dimensional half-life radius. So I've got my rho s RS here. I just have to multiply by 2 pi 3D half-life radius squared. I multiply that in, and this is what I get. And just compared to the previous slide, this is the same relation, except in that case, this was 2.5 instead of 1.95. So I'm off by about 30%. But again, it's not surprising I'm off by a little bit. I assume the Plummer profile, I set beta star to 0. That's all the stuff which gives me the order 1 slot. So what we can see then is that solving the spherical genius equation is giving me something consistent with the half-life mass. We can also kind of get a hint of why it's, at least part of why, it's insensitive to some of these variations. For example, let's say I didn't use a Plummer profile. Let's say I use a King profile. All it would do is it would change this function, but it wouldn't change the parametric dependence. So instead of this integral giving me 2/3, it would give me some other number, okay, which would be off by some order 1 factor. But it wouldn't change any of the parametric dependence. Again, as long as I'm in this kind of limit here, there's going to be this one parameter which it can depend on, okay, and everything else. And so the actual detailed explanation for why it's true ends up being much more complicated because you end up finding that at the half-light radius for all these profiles, there's a certain slope at which the total mass, which the dark matter mass, or I'm sorry, the stellar mass distribution varies, and that's exactly what, roughly where you end up canceling all the dependence on the velocity anisotropy parameter. So it ends up being a little bit more complicated, but at some level it amounts to almost a dimensional analysis argument. Because you say, what are the parameters it can depend on? There becomes a dark matter parameter and there becomes a stellar parameter, and then everything else is just an order 1 number. So that kind of tells you then is that this is matching the half-life mass. But it also has me that one quantity which I thought I could reconstruct from Jeans modeling, I can basically just reconstruct from the half-life mass estimator just as well. Okay? And that is robust to all those degeneracies, which I didn't know how to control with Jeans model. So we can ask then, how well does this work? How well does this scaling relationship replace what I would learn from Jeans model? So to address that, what we can do is just do Jeans modeling for 9 dwarf spheroidals with 20 or fewer identified member stars. So these are the ones we chose. There are a few dwarves which have fewer than 20 stars which we didn't use, basically because some of these coarse-grained stellar observables, like the line of sight velocity dispersion, aren't well measured. You only get an upper bound on it because you just don't have good enough kinematic measurements. I also didn't include Ursa Major III because I'm going to do that separately, since we're not really sure if it's a dwarf or not. So what I've plotted here are the posterior distribution of rho SRS in units of these coarse-grained stellar observables, RH and the line of sight velocity dispersion. And these values I just get from Andrew Pace's local volume database, which just collects a bunch of coarse-grained stellar observables for all the stars and star clusters which you can imagine. So I'll plot, so these purple regions are the 90% credible intervals for the posterior rho SRS in units of G Newton, RH, and line of sight velocity dispersion. This black line is what I would get if I just used the half-life mass estimator, assuming the scale radius was large compared to the half-life radius. And so what you can see is that this pretty much matches up. It pretty much gives you all the information you would have had. So one way to think about it is that of the 9 stars I did, of the 9 systems I did, in 7 of 9, the half-life mass estimator lies within the 90% credible interval. That's just about what I would expect, right, if it was right. So what you get from Jeans modeling is basically not any different than what you've gotten from this scaling relation for these ultra-faint dwarfs. Mm-hmm. Mm-hmm. So one way I would look at it is, if it's outside, it could mean that this is one example where the scale radius just isn't large compared to the half-life radius. Okay? Because I haven't given an argument that the scale radius is much larger than the half-life radius. What I've really argued is that in any of these cases, I don't have enough stars to tell the difference. Okay? So in all these cases, what I find is that if I just look at that, what a half-life mass estimator would tell me, assuming the scale radius was much larger than the half-life radius, it fits within what, the posterior distribution of what I actually get from Jeans modeling. So Jeans modeling can't really tell me that that's true or not true. Although it might not be true for any particular dwarf. And it could be true for some and not others. Mm-hmm. Yeah. Excuse me?
So that can also go down to connect C.
that could also, like, those assumptions could be bad assumptions. Yeah. Oh, the weighted mean was just to say, if I just plot, what would the weighted mean look like for all of these? If these were all, let's say these all had the same RH over RS. Let's say they were all really small. And I tried to find a weighted mean for this, right? Would that be consistent with the half-life mass estimator? So this is just, in some sense it's not really that useful. It's just a question of, if these all had the same value of RH over RS, and I tried to combine all these analyses, what would I get? Would it just be, how consistent would it be with, this weighted average? Yeah. Yeah. Or, this is weighting all, so one way to look at it, each individual one tells you how consistent each individual one is with the half-life mass estimator. Right, because I've combined all of them together, yeah. Yeah, so I've done the weighted mean, the mean weighted by all of the posteriors of this, yeah. And it turns out, even though it's kind of variant here, if you include, the uncertainties in sigma and RH are actually pretty large. Even the weighted means, once I include that, are not going to be very far off from the half-life mass estimator. And so we can then ask, how do I then use the scaling relation to just get a scaling relation for the J factors? So again, we can think of the parameters we now have as rho s rs, which I can get from the half-life mass estimator, and Rn, the edge of the integration region, which I'm setting by my aperture size. And so, kind of my expression for the J factor, once I plug in the scaling relation, then kind of looks like this. So I just get a scaling relation in terms of these coarse-grained observables, which I can just grab from Andrew Pace's database. Now, one thing you might notice then is that the J factor, as you might expect, increases with theta. So you might ask, why don't I just make theta larger? The scale radius is bigger. Could I get a larger flux just by making a larger observation? It turns out that doesn't actually help you very much. Because as you see, the J factor only scales linearly with theta. But your background goes like a solid angle, so it's going to scale quadratically with theta. So signal significance will be signal over root background. That's actually not going to change very much. So you don't actually gain much by going to a larger angular size. You might as well just stick out with, the minimum you choose based on your point spread function. Yeah. Yeah. Well, oh yeah, that's right. Yeah, right. But you could say, depending on how far away it is, instead of 1 degree, make that go to 2 degrees or something like that. Yeah. Oh yeah, that's right. Yeah, that's right. Yeah, that's right. Mm-hmm. Yeah, I'll assume a small angle approximation all over this place in any case. And so the last thing we could do is try to apply this to Ursa Major III. And again, get back to that question of, can I really trust the J factor, even the uncertainties in the J factor? Because the thing with Ursa Major III is that even though I went to the low end of the uncertainties, it's still a pretty big J factor. It becomes an important dwarf to look at. But can I trust any of it? And even the people who first did this analysis, who discovered it, first did the genes modeling, they gave reasons to be suspicious of it, because they said of the 11 member stars, 2 of them appeared to be velocity outliers. So their velocities were pretty large. It wasn't clear that there wasn't some problem with these stars. If you include both of them, then the square root of the line of sight velocity dispersion is like 3.7 kilometers per second plus or minus. If you remove one of them, that drops to 1.9 kilometers per second plus or minus. If you remove both of them, then you only get an upper bound on the line of sight velocity dispersion. So what we can do is then do genes modeling, but now find the posteriors on the half-life mass. Okay, so the dark matter mass contained within the half-life radius in units of these stellar observables, which again were reported by the discovery paper, so we can just use the results they have. If you plot those posteriors, then the central value you get for this ratio is like 0.04, plus or minus. But what the half-life mass estimator told you is that that coefficient should be about 3.25. So this is way off what you should get from the half-life mass estimator. And genes modeling, that's the one thing it's supposed to be able to reconstruct. So that could be a hint that these really are velocity outliers, that they've biased your line of sight velocity dispersion upward, and that's drawing this ratio down. So you say, okay, let's remove the highest outlier. In that case, if you redo it, so redo Gene's volume on the 10 remaining stars, this goes up a bit as you'd hope, but not enough. It's still very far discrepant from what the half-life mass estimator tells you. So then the next thing you could do is if you remove the last one, well, then you're stuck, because on the one hand, you only have an upper bound on this. So you can satisfy the half-life mass estimator, because you can say maybe the line of sight velocity dispersion is really small, and that makes this consistent. But if you remember, the J factor is scaling with the line of sight velocity dispersion, which means if you now only have an upper bound on this, then you have no lower bound on the J factor. So the J factor not only could it be much smaller than you were thinking, it could be arbitrarily small. You have no idea how small it could be. Right? So you no longer necessarily have a reason to think that this is a great target for dark matter searches, that it's going to set tighter bounds than anything else you've seen.
So how do you take to
They didn't give it, but there's some more recent news, which is the last slide. So more recently, another collaboration of people, which includes some of the people who were on the original discovery of this, they kind of did some updated new observations using Keck. Okay? So now I have 16 member stars identified, but 4 of them appear to be binary. One is confirmed to be a binary star, 3 are candidate binary stars. But the key thing is the one which is confirmed to be a binary was one of the original velocity outliers, the largest outlier. And now you might see why the velocity is too large. Because you could be confusing the motion of the stars around their mutual center of mass as opposed to the center mass of the dwarf. So that could have biased your measure. If you remove those binaries and now try to redo the line of sight velocity dispersion, you now find you only have an upper bound at 95% confidence. So you no longer have a measurement of it. You just have an upper bound. Well, now they say that there are 2 stars, yeah. But it's still hard, again, remember, only one is even a confirmed binary. The other 3 are candidate binaries. So it's not that you have such precise measurements that you can say, okay, I've measured their velocities with enough precision that I can separate out, I can figure out the center of mass velocity. All you can figure out is it looks like there are 2, right? But you don't know, you can't measure, you can't remove that uncertainty in it. So, yeah. I'm sorry, could you repeat the last part?
So when you have some other problems, right? Mm-hmm. Sort of normal. So there also, do we assume that all stars are like on their own and that some of them can be binary?
Oh, in general, you expect some fraction to be binaries. In fact, I think people who look at these galaxies say there's some fraction, which you expect to be binaries. I think having 4 out of this is consistent with what people tend to expect. But I think it is something that when you try to do the kinematics, you have to account for that because you would have biased your sample in doing that. So they have to account for that. So you have to identify these binaries. Yeah. Mm-hmm. Yeah. Well, one way to look at it is so I think there are a few things that go into this because you've removed one which had a large thing, but now you only have 10 stars. Right? So you're doing Gene's volume with fewer stars, right? And you can see, your uncertainties are still large here. So, like even when this goes down, the uncertainty in it doesn't go down. So there are a lot of things, it becomes harder then. And so what these guys say is that, again, this doesn't show that this is not a dwarf galaxy. What they put is there's no positive observational evidence for the presence of dark matter in this system. Now, this is just using stellar kinematics. They also look at the metallicity, and they tend to find that these stars are low metallicity with a low, small dispersion in the metallicity. And they say, yeah, more consistent with a star cluster than a dwarf spheroidal. I won't say more about that because I'm not an astronomer. But in some sense, what this confirms what we kind of found using the half-life mass estimator, which is we can't even really set a lower bound on the amount on the dark matter content in here anymore. And so maybe I'll just end with the conclusions, saying that, nearby ultrafaint dwarf galaxies can be a promising target for dark matter indirect detection, especially in the coming years when we expect to find many more of them, and some might be nearby. But we need to understand the dark matter distribution, and there are limits to what Jean's modeling can tell us when you have so few stars. And much of what it can tell can also just be determined by these simple scaling relations. And a nice application of those techniques is understanding Ursa Major III unions. That's all I have there. Well, so let me ignore the systematics in that order one factor in the half-life mass estimator. Then what you would say is, well, you're right. So here you'd say, I still have some uncertainty in these quantities. Yeah, it comes from measurement, this comes from measurement, even this comes from measurement. So I could use that to generate an uncertainty band. Yeah. But again, that's ignoring that order one factor. But then again, I think a lot of these will be much larger than that. Yeah. Yeah, there's a D. People call it a D factor, but yeah. Yeah. So that have a slightly different form than this. Yeah. So I guess the idea is that in that case, it's not going to go like rho SRS. So yeah. So then you would have to sort of redo the calculation and get a slightly different scaling relationship. But yeah, one can do that too. One way to kind of think about it is you'd kind of do an integral like this. Here. Yeah, just be rho. But you kind of say again, you kind of know what it has to depend on. It has to depend on rho SRS, because that's the only parameter of the profile. And then it's got to depend on your cutoff. It'll be a little bit different, because one thing is, because this goes like density squared, the tail here falls off dramatically. It's not it becomes more logarithmic for the dwarf. So things like tidal radius and stuff like that can be more relevant for that case. So it becomes a little bit trickier, but yeah, at some level it holds still.